This is part 2. We left off, it's like a series. We left off last episode with this situation because the lesson ended. Now I'm just going to draw our diagram a little bit nicer, which I've already done here. And what we wanted to do was prove that the angles of a rhombus were bisected here. So we had a little bit of a discussion last time of how can we do stuff that we used last time. Whoops, not that one. But like the dot product bit. But that's not really going to be helpful, those properties, because yes, we know that these angles intersect here at 90 degrees. And I think I glossed over the geometric one as well because I think, oh, everybody knew. But hopefully you do realise, because yes, they are 90 degrees and these guys are the same and then these ones are the same, and because we've got it's a rhombus, so those are the same, they're congruent triangles everywhere, right? So side, side, side means that this angle would then be the same as this one because they're the corresponding angles. So that's why we glossed over the geometric one. To the vector one, what we're trying to do is we want to find an expression for that angle, an expression for that, and hopefully they're the same. Okay, and I just erased what we had on the board last time, but we said, well, we tried the dot product thing, so the only other bit that deals with angles was our cos formula, right? And I think, Sam, you were going, we could go find an expression for this one, for alpha, and then if you could prove that that one was 2 alpha and say that was double whatever, that would be a little bit, and I thought, that's a great way to think of it. But that gets us a little bit fuzzy, I guess, where we've got a cos alpha and then a cos 2 alpha. So let's have a go at finding an expression for cos alpha and cos beta, and let's see, can we say that they are the same? And if we can, therefore that diagonal bisects. Agreed? So you might be going, what is Sean about? Well, remember your angle formula. I'll just do it over here, and I know we have it in terms of A and B, and there's all A's and B's here, so bear with me. But do you remember it was A dotted with B all over AB? Length of A times the length of B. So in our situation, we're going to first look at, get my colour coding going now, we want to look at this blue vector going on there. Agreed? So it's going to be A dotted with A plus B. I think we had this from last lesson, all over the length of A and the length of B. And we go, yep, okay, sure. But what can we do with that? Not an awful lot. We can look at the top and say, well, that's A dotted with A and A dotted with B. And before we sort of go, oops, stuffed up the bottom one. That should be A plus B, correct? Before we sort of go, this isn't really getting me anywhere, we just want to look at the other side. I mean, we could rewrite that one. What's A dotted with B? Not 0. It's the modulus of A squared. Anyway, that's as far as we can sort of go with that. So now, can we look at cos beta, which is now going to be, yep, that's now going to be, oh, I did the wrong colour, hey, we'll go green. So now it's going to be this one and this one. So that's now going to be A plus B dotted with B all over the length of A plus B dotted with the length of B. Multiplied. I'm getting a little bit excited. So can you get that? I want you to play with this. Have a look at it. Don't tell your neighbour and tell us why. Yeah, okay, we can say they're the same. Okay, so people very, very nicely went about their business and we said, yes, we've got this happening, and then downstairs we've got the length of A plus B times the length of B, and we sort of go, well, we did what we did on the other side, and that's that one squared all over A plus B. Now, once again, we hit a bit of a blockade, but that's when you have to go back. Are there any more clues in the question that we have? And remember what we just said, and everyone went, oh, was that it's a rhombus. Okay, and what's so special about a rhombus? What makes a rhombus is that these lengths, now the length A doesn't equal B, but the length of A will equal the length of B. And so therefore, what we have now is we can say, well, because the length of B squared would have to equal the length of A squared, so we can say that that is the same. Would we agree? And so downstairs, now we've got the modulus of A plus B. I mean, they're the same. And once again, the length of B is the same as the length of A. I mean, I guess if we're doing nice things here, since A equals B, rhombus. Ha, bisect. Okay. Again, an example of do something, have a look, you know what you're trying to prove, look at the information that you have. How does that help us? Technically, we would then also have to repeat the process to prove these ones, bisect. But it's the same thing. Instead of you could go B across there plus A take B, and it'll be exactly the same thing. So do we have to do it? Great. That was a no. That was a shake of the head. Are we happy? All right. Did you have a go at starting A and B for this? So I know you're tempted to just go straight to this little bit and say, okay, yep, O to X, it's going to be OA plus AB there. So OA, we know nicely, is A. What is AB? So A to B. So A, I like to draw the arrows in there, right? And remember, so if I want A to B, I have to start with A and then go there. Okay, so it'll be minus A plus B. Oui? Okay, and I could then just tidy that up. So a whole A take a half A is a half A, so it's a half A plus B. That's what you got? Yes. You remember this, do you? Are you doing it again? Because I think we'll have to use it. Okay, and then BZ. So B to Z, we have to start then here. BOOZ. So if you're looking at your, this is why these are pretty important. You can see the end ones are the B and the Z, and you know that it's happening because you've got those, the O's in the middle. Same with this, we knew that was good. Then you can go away and do what you need to do. Okay, so B to O, OB was B. So we're gonna, I mean, again, you could write O minus OB if you wanted to, or we could just go minus B. But at least some notation of what you are doing is definitely needed. Okay, now OZ. Oh, that's nice. Yep. So again, if you wanted to go half OA, you could, but I'm now being a little bit naughty and just going a half A. But at least I've got one line there. Okay, so everyone agreed with that? And then we wanted to do number 2. It doesn't say it's in the middle, it's just part of this. So would you agree, let's start with one way that we could find OP. Give me one way.
I did intersecting, but that didn't really work.
What do you mean intersecting?
So I did 1/2 A plus B equals minus B plus B.
Hang on, 1/2.
So OX equals BZ.
We can find OP in a whole lot of different ways, right? We can say that it is a fraction of OX, yes? But we could also find it as OZ plus ZP, which is a fraction of BZ. We could also go OB plus BP, and same thing, fraction of. So, up to you. What would you like to go with? What would you think would be the easiest ones? Yeah, I would probably go OB plus BP and find the other expression. And we could do all three and you have a look, but I think we'll just go with those ones. Do you reckon? So we start by saying, am I recording? Yes, I am. So we'll start by saying, would you agree that it's a fraction of OX? Now, what fraction is it? So it's a multiple of. It could be a half times OX. It could be a quarter, 3/4 times OX, right? But we don't know what that is. So we're just going to, you want to call it K? That's the normal. So it's OP is going to be K lots of OX. And the reason that we're also using OX is that we've got this expression here from part A. Okay, so we can say, well, this will now be, oh dear, K lots of a half A plus B. Yeah? So that we're all sticking on the same page, we now need another scalar when we do this one. So OP, if we go that way, it's going to be OB plus a fraction of BZ, which we have here also. So we use K here. What would you like to use? Okay. Really?
C.
M. K and M.
I don't know, what would you use?
I know.
L.
Yes.
Okay.
But then I wouldn't use L. I would use L, but I wouldn't use L for you. I guess M would be the next one. Like I do my L's like this, and you can mock me, but
I do like that as well.
oh, there you go. But some of you go stroke, and then you could go 1. So okay, we'll go M. I was going to say normally I go M and N, but there you go. So it's M lots of BZ. We happy with that? As happy as you can be? Okay. What would be my next line?
So
OB is B. Yep. And we've got our BZ up here. Yep. M times
minus B.
and it would be understandable if you were then going, hell's bells. This is making it worse. I'm going to give up. But Mr. Equating over here, this is where our equating can go, because what we are saying is that this expression has to equal this expression. Now, I understand there's A's, there's B's, there's K's, and there's M's. It's like, come on, what's up with that? What I would like you to do is I want you to look at the coefficients, right? Look at the coefficients of A on this side. Look at the coefficients of B on both sides. So as a tip, what would be the coefficient of A on the left-hand side? I'll write that better. I will write that better for you, my people. So what we're saying is that K times a half A plus K times a half B must equal this thing over here, B plus M times minus B plus a half A. Do you agree with that? So now what we're going to do is we're going to look at the coefficients of the A and the B on each side. So what's the coefficient of A on the left-hand side? Half K. And that has to equal, what's the coefficient of A on the right-hand side? Hell's bells. Oh, well that's not too bad. Because now we know K equals M. Now do the B and see if you can actually solve for a value for K and M. So hopefully you solve for B. Okay, we said we wanted to find OP, so now we're going to look up here, and so therefore OP would be 2/3 of OX. Is that what we wanted? Oh, sorry. We wanted it in terms of A and B. No, so we don't want that. Put it in this one. Because we want it in terms of A and B. So 2/3 times 1/2 times A plus B. Last time I checked, that can cancel. Ding, 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 ding. So 1/3 A plus B. Oops. So sorry, people are working on C, but we're just saying with D, I think you have to use this because part D is saying, can you prove that P is a common point? Now we've already proved that these medians go through P, that they're straight lines. Well, that was given, I guess, in the question. So what we're trying to prove is that P would be a common point if APY was a straight line and it didn't go APY. It was straight. So how do we prove that? And as Tom said, it's going to be if this vector is then a multiple of that vector. Okay, or that vector is a multiple of that one. And especially since you've got these things here, y to p, p to a, so I would imagine one would have to be, was one a multiple of the other?
What's a median?
So the medians are these from a vertex to the midpoint.
So
It's a theorem.
what?